In the discrete time setting, the Chapman-Kolmogorov equations reduce to a single one-step transition kernel governing the dynamics of the whole process. And in particular, if we also have discrete space, we end up needing to analyze a discrete linear dynamical system, that is, taking powers of a fixed Markov matrix. What about in continuous time? For a continuous time, homogeneous time Markov process, as we've seen, the Chapman-Kolmogorov equations reduce to this, the semigroup equation. Now, we've seen this kind of equation before. In fact, when we began our discussion of some stochastic processes and dealt with the Poisson process, we saw that the interarrival times of the process, necessarily having a memoryless property, had to be exponential because of this semigroup property that uniquely defines exponentials in the appropriate context. That context was where these were functions of s and t taking non-negative real values that we already knew had some kind of regularity. Here we have operators acting on the space of bounded measurable functions on our state space. Is it too much to hope that this equation will similarly dictate that qt has to be an exponential of something? Well, it does turn out, yes, that's too much to hope in general, but in a lot of cases that we'll spend a lot of time over the next many lectures discussing, it really does work out that way. Let's start discussing the case of a finite state chain. Let's just label the states of our process 1 through n. Now in this case, the space of bounded functions from s to r is easily identified with r to the n, and therefore qt, which is a linear operator on that space, can be identified as a matrix. Now, one way we could form such a qt would be if we did have a fixed n by n matrix, and qt was the exponential of that matrix. Just to be clear, we can define the exponential in general here by its power series. Here, the powers of an n by n matrix are perfectly well defined, and this power series will make perfect sense for matrices here just as it does for real or complex numbers. It will converge everywhere to a matrix-valued analytic function. If we do have a family of operators that are defined as the exponential of some generating operator A like this, then of course at time 0 the value is the identity matrix, since e to the 0 is the identity matrix, as we can see from this formula here, with all terms n greater than or equal to 1 being 0. And also q of t plus s, which is e to the t plus s times a, is going to be e to the ta, e to the sa, which is qt, qs. The semigroup property will hold. Now let's be very clear and very careful. If a and b are two matrices, the equation e to the a plus b equals e to the a, e to the b is usually false. It's true pretty much only in the case where a and b commute with each other. That is, ab equals ba. Well, in this case, the two matrices are a multiple of a and another multiple of a fixed a. And those do commute with each other. So we do find that this semigroup property holds for exponentials like this. And proving that, if you like, is just a matter of using the power series expansion and using the usual proof that the exponential map has the semigroup property, which involves expanding a binomial inside here. And since the matrices SA and TA commute, that binomial theorem expansion is going to produce the same result. So here's our terminology. If our semigroup of transition operators has the form e to the TA for some operator A, we call that operator A the Markov generator. Not every continuous time homogeneous Markov process has a generator, and in fact, with this sort of boneheaded definition that we've given here that's a little vague in the case where we don't have a finite state space, some of the ones that we would most like to don't have a generator. We will see later that they do have a generator, we just need to be a little more generous about what we mean by that. But not getting into those technical details just yet, supposing one exists, how do we find it? Well, I guess we need to take the logarithm of qt, but that's really quite tricky. Instead, there's a much easier way to do it, which is to say, hey, if qt is e to the ta, why don't I just differentiate it as a function of t? Again, this power series defines an analytic, therefore certainly smooth, function of t, taking values in the matrices, and using the usual calculus formulas, we can quickly check that this derivative is a e to the ta, which is the same thing as e to the ta times a, again, because ta commutes with a. Therefore, we can recover the generator a just by taking the derivative of the transition operator qt at time 0. Now, we're being a little bit fast and loose here because the transition operators are only defined for t non-negative, so we can't really take this derivative. So when we write this, we really mean that we're taking the right derivative. Of course, if there is an a so that qt has this form, then we would be able to extend it backward in time as well, at least in this finite state space setting. Okay, so in principle, we know how to find the generator now, and now we'd like to understand what kind of properties it has. Well, the transition operator qt, which we're thinking of here as a matrix indexed by states I and j, has some properties which, as we discussed in the dual discrete time case in the last lecture, has some properties that pin it down. Since this is just, in this discrete space setting, the conditional probability that the process at time t is in state j, given that it started in state I, this is a probability and therefore is non-negative. Moreover, we know from the law of total probability, if we like, or alternatively from the fact that this is a probability kernel, that the row sums of this matrix are all 1. So it stands to reason that these two kinds of conditions will translate into two kinds of conditions about the generator when it exists as well. And we can see that it does quickly as follows. The matrix entries aij are just going to be the matrix entries of this derivative, but that just by definition at time 0 is the limit, and we'll even take the right derivative, t going down to 0, of qt of ij minus q0 of ij, but q0 is the identity matrix, and so here are its entries, divided by t. So what can we see from that? Well, for starters, if I is not equal to j, then what we have here is just the limit of qt of ij over t. And that's greater than or equal to 0 for all t, and therefore that limit will be greater than or equal to 0 in this case. So the generator has non-negative entries off the diagonal. Now what can we say about on the diagonal? Well, we can say something about that by looking at the row sums. If I take the row sum of the ith row of aij, that's going to be the derivative of the row sum of qt at t equal to 0. In other words, it's the limit as t goes down to 0 of 1 over t times the sum over j of qt of ij minus delta ij. Well, we can distribute this sum through these two terms. The sum of delta ij is 1, and so this is the limit as t goes down to 0 of 1 over t times the sum over j of qtij minus 1. But the row sums of q are all 1, and so this is just 0. So that is, the condition that the transition matrix has row sums equal to 1 tell us that its generator has row sums equal to 0. So that will tell us in particular that the diagonal entries must be non-positive, since the sums are 0, but all of the off-diagonal terms are non-negative. All right, so to summarize, what we've shown is that if A is any n by n matrix, and we define qt to be e to the ta, then those qt's are the transition operators for a time homogeneous Markov process if and only if that matrix A has non-negative entries off the diagonal and has row sums equal to 0. Well, actually, we only showed the only if direction there. If the transition kernel has this form, then that matrix A has non-negative entries off the diagonal and row sums equal to 0. That's what we just showed on the previous slide. The converse, that if you have a matrix A that satisfies these conditions, then this is a Markov transition kernel, is on your homework. But again, let's emphasize that this doesn't say that every Markov process has a generator like this, even for a finite state process. In fact, that's just not true in general, and here's a simple counterexample. Suppose that we have, as our Markov transition matrix, a matrix all of whose rows are equal to some fixed probability mass vector, nu. This is a Markov matrix. Remember, a Markov matrix is going to be uniquely specified by having entries in the unit interval with row sums equal to 1. Well, of course that's true if all the rows are equal to a fixed probability mass vector. So just to be clear, what I'm saying here is that the ij entry of this matrix is equal to nu of j and doesn't depend on I. Well then, actually, if we define qt of I and j to be the ij entry of that matrix, that actually is a Markov semigroup. How do we see that? We just need to show that qs composed with qt is qs plus t. And to do that composition, since we're just doing matrix multiplication, that means taking qs of ik times qt of kj and summing over k. That gives us the ij entry of the composition of qs and qt. Well, that's the sum over k of pik pkj. But pkj from over here doesn't depend on k, it's just constantly equal to nu of j. And so that comes out of the sum. This is nu of j times the sum over k of pik. But the row sums are all 1, and so that sums to 1, which means that we just get nu of j. But nu of j is, again, right from our definition over here, equal to pij for each I, and that is the transition kernel at each time, as we've defined. And so we do get the Chapman-Kolmogorov semigroup property holding here. Now, you may pause and say, wait a minute, what about the condition that q at time 0 is the identity matrix? It looks like it would have to be p again here, but actually, all we're specifying here is that this is the value of qs at each strictly positive s. We can then just declare that at time 0 it's the identity matrix, and then we satisfy our Chapman-Kolmogorov equations. Of course, what that means is that this is not a continuous function of t. It starts at the identity and then immediately jumps to this matrix P, which is certainly not the identity matrix, if n is bigger than 1. So that's yet more evidence that we will not have a generator here, because if we have a generator, this is a really nice function of t at t equals 0 and beyond, whereas this function is discontinuous at t. This Markov chain does not have a generator, and it has some pretty bizarre properties, as you can quickly work out. The transition kernel from time s to time t is q of t minus s, and so that means that the probability that x at time t is in state j, given that x at time s is in state I, is just constantly equal to this distribution nu of j, independent of s and t and I. Well, since it's independent of I, that means that this is also the probability that xt equals j. And so what that says is that the probability that xt is in some particular state is independent of whatever the state xs is in. In other words, it says that the whole uncountable family of random variables xt are independent and identically distributed with law nu. Now you might think that that must be some kind of contradiction. How can you have uncountably many independent, identically distributed random variables? Well, you're right to be skeptical that something funny is going on here. This is a very degenerate situation, but you can also use the tools that we've developed in the last few lectures to see that actually, yes, you can construct such a family of independent random variables indexed by positive time. Now, it turns out that this kind of example here, where we have discontinuity at the origin, that is the only obstruction to having a generator. It is in fact a theorem that if our Markov semigroup Qt is a continuous function of t all the way down to 0, then a generator does exist. In other words, we have the property that if this is a continuous function of t, then it's also a differentiable function of t. And we can use an argument similar to what we did for the uniqueness of exponential distributions having the memoryless property to derive the exponential nature of the semigroup. We will see arguments about that in future lectures. I do want to point out that there are subtleties. We are here considering the case of a discrete state space with finitely many states, and so this is just a matrix. We can define this by exponentiation, and continuity is not a controversial property. We know what it means for this to be a continuous function of t, taking values in matrices, because we can just identify the matrices with Euclidean space and put a Euclidean norm on them. But it actually won't matter what norm we put on them, because all norms on a finite dimensional space are equivalent to each other. But what if we have infinitely many states? Or what if we have a continuous state space? Then what does it even mean to say that this is a continuous function of t? Well, if we make the appropriate definition of continuous, and if we are appropriately precise about what we mean by this being equal to e to the ta for some operator a and where that operator lives, then we will be able to show a similar result, that if we have a semigroup that is a continuous function of time, it will have a generator in the appropriate sense. You'll have to stay tuned to see what we mean by that in more sophisticated contexts. For right now, let's stick with the discrete space context, although bump it up to countably infinite, and return again to our favorite discrete space continuous time stochastic process, the Poisson process. For the Poisson process, we can explicitly write down the transition kernel. We've sort of done that in the past, but let's do it fully right now. So what is the transition kernel going from time s to a larger time t, of going from state m to state n? Well, that is the probability that at time t we're at count n, given that at time s we were at count m. Now, this is an independent increment process, and we have a general formula for the kernel for those, but we can sort of derive it directly here in this discrete setting quite quickly, just to show you how this works. Let's write nt as nt minus ns plus ns. And now, once we've done that, notice that we're conditioning on the event that ns is equal to m. So let's therefore write this as the probability that nt minus ns, we'll keep that, ns as itself, plus m is equal to n, given ns equals m. Now, the benefit of doing this is that nt minus ns is independent from ns, which is the same as ns minus n0 because that's 0. So using our independent increments, that means that this is also the unconditional probability. This is the probability that nt minus ns is equal to n minus m. And now we can write out explicitly what that is, because nt minus ns is a Poisson random variable with rate lambda times the length of the interval from s up to t. And so we have this explicit formula for our transition kernel. Now, how about the transition semigroup? Well, we get the transition operator just by integrating the transition kernel, and that means summing in this discrete context. So this is the sum over all states, that is non-negative integers, of qt going from k to n of f at n. Now, k is fixed here, and if n is less than k, then you can't get from k to n in any positive time. So these terms are all 0 when n is less than k. And so that's just the sum n bigger than or equal to k of qt, which we have a formula for here. We're utilizing the time homogeneity and noting that this is just a function of t minus s, so we're replacing it with just t. So that gives us e to the minus lambda t to the n minus k over n minus k factorial f at n. And now let's reindex this sum. Instead of starting at k, let's start it at 0. In other words, we're replacing n with n minus k. So that's the sum n going from 0 up to infinity, e to the minus lambda t to the n divided by n factorial. And instead of n inside the function, it's k plus n. So there we have the explicit action of Qt, and if we want, we could now verify by simple power series operations that the Qt do form a semigroup. But does this semigroup have a generator? Well, we saw that if there's a generator, we can recover it by this formula here, that is, differentiating at time 0. That tells us that if there's a generator, there's a unique one. So, can we do this differentiation? Well, the first question is, what exactly do we mean by this? Here I'm suggesting that we fix k and then differentiate this function of t, although before we were differentiating the whole operator valued thing. And if we were being very careful, we'd have to draw a distinction between those two. But let's not be careful right now. Let's just do the calculation and then see afterward if we were justified. So let's differentiate at any time. We have our function of t here, and I'll write it as a product. We have this overall factor of e to the minus lambda t, and then we have this power series in t over here. We know how to differentiate power series. At least on their domain of convergence. And in fact, this power series converges on all of R. Of course, we're supposed to think of t as positive, but right now that wouldn't make any difference to the calculations. And the reason the radius of convergence is infinite is because f is a bounded function. Those are the kind of functions we use in our calculations here. And if we have a bounded function here, then of course this is going to converge everywhere by the ratio test, if you like. So it's a everywhere convergent power series, and we can therefore differentiate it term by term. We'll start by using the product rule, and so we differentiate this times that, and then multiply this times the derivative of the power series and add those up. Here's the derivative of the exponential term, and here's the term-by-term derivative of the power series. And we'll just make a quick observation here. First, when n is equal to 0, we have a 0 here, so that term is not really there. This sum really starts at n equal 1. And then once we do that, we can combine the n over n factorial into an n minus 1 factorial. So that's lambda t to the n minus 1 over n minus 1 factorial. We'll take the lambda out and group it with e to the minus lambda t to match what we've got going on over here. And now we're going to reindex the sum. We'll start it at n equals 0, which means replacing n with n minus 1 everywhere. So this second term here actually becomes lambda e to the minus lambda t, sum n going from 0 up to infinity, of lambda t to the n over n factorial, and the only change is that the n now becomes n plus 1, so we have k plus n plus 1. So combining that with that, and then referring to the original formula for the transition semigroup, what we see here is that the derivative at any time t is given by, in the first term, we just have minus lambda times qt acting on the function. And in the second term here, we have lambda times qt acting on not the original function, but the function incremented inside. That is, we shift the function by 1, and then apply lambda times qt. Well, that's good news, because we can set t equal to 0 in this formula. Q at time 0 is the identity, and so what we get is that the derivative at time 0, which should be our generator a, just acts by taking our function f and taking the finite difference between its value at incremented k plus 1 and k, and then multiplying that difference by lambda. And so defining the operator a this way, which is a perfectly nice, well-defined operator on bounded functions, returning a new bounded function, then what we've shown here is that the derivative of qt applied to f is qt applied to af. That is, we apply qt to this operator a, shifting the function and then subtracting the function's value. And that's the same thing as applying qt and then shifting the function. That is to say, the action of shifting the function by 1 inside here does not influence how t acts in this formula. So qt and a commute with each other, which we knew would have to happen here since a was the generator. So does that mean that qt is equal to e to the ta? That's what this would say if f were defined on a finite dimensional space. The solution to this differential equation with the initial condition that Q0 is the identity, as we know we have here, is uniquely the exponential, the matrix exponential, if you like. Now, this is an infinite dimensional example, so it's not even clear what we mean by e to the ta, except that we can make the same definition as usual and define it by the power series. Now, I'm not saying that you can take the powers of any arbitrary operator in an infinite dimensional space, add it up, and expect that this is going to be a finite sum. In this case, we could do that, in fact, by putting the right norms on the spaces, but actually we can do it much more explicitly in this case, because the nth power of a is something that we can explicitly write down as a nice operation, and then we can do this sum and see if the resulting expression matches up to our original Qt. So let's go ahead and do that. And in so doing, we're again going to use the important fact that if I have two operators that commute with each other, then e to the t a plus b is equal to e to the ta e to the tb. Now that's going to make sense here, provided that this power series here converges in any appropriate sense, and the usual binomial argument that we alluded to earlier will do the trick once again. So to check if this is true, we need to start taking powers of our generator A here. And to do that, it's going to be convenient to write it, like here, as a difference of two operators. That is, it's going to be t minus I times lambda here. I is the identity operator, that is, this term here, I of f is equal to f, and t is the translation operator, t of f is equal to f shifted by 1. Tf at k is f at k plus 1. Then we can write af here as lambda times t minus I applied to f. Well, we could either do binomial expanding these out or use the property that we just stated, but because these two commute with each other, e to the ta is therefore going to be just e to the minus lambda ti times e to the lambda t times the operator t. And e to the minus lambda ti is just e to the minus lambda t dot. That is, the action of that operator on a function is just to multiply it by e to the minus lambda t. So in order to calculate the exponential of this operator, we just need to calculate the exponential of this operator and then multiply the result by e to the minus lambda t in the end. So in order to compute that, via its definition of this power series, that means we need to compute what t to the n does. Well, tf at k is f at k plus 1. That means that t squared f at k is t applied to f at k plus 1, which is f at k plus 2. And you can quickly see, by induction if you like, that the nth power of t just shifts f by n in the argument. Thus, this sum here is exactly the sum lambda t to the n over n factorial f at k plus n. And that, except for this missing factor of e to the minus lambda t, is exactly our definition of Qt, as we established on the last two slides. So we've really barehandedly proved now that the Poisson process has a Markov generator, and that Markov generator is explicitly given right here. And it's very suggestive of a connection between the generator and the action of the process in this case. What does a Poisson process do? It has jumps of size 1, and those jumps occur at rate lambda. Here we have a jump of size 1 in our test function occurring at rate lambda. Now, we can put this in the same kind of language as we did in the finite state space example. In order to talk about a Markov matrix here, we would have to have a basis for our space. So let's express bounded measurable functions on the natural numbers, that is just bounded functions, in terms of the basis of indicator functions of the integers. In other words, I'm just expressing any bounded function as a sum of its value at k times the indicator of k. Of course, if this is literally a linear algebra setup, then I can only have finite sums, and so that doesn't really capture all bounded functions here. But let's ignore that detail for the time being, just to get the right picture here. In terms of that basis, the matrix of the generator A can be written as follows. The basis element 1k gets mapped to 1k plus 1 minus 1k times lambda, and so that means that we get a minus lambda in the kk entry and a lambda in the kk plus 1 entry, and zeros everywhere else. That is to say, it's minus lambda times the identity plus lambda times the shift by 1, which is, of course, the matrix of that operator T. And what I want you to note about this matrix is that its row sums are indeed all 0. They're all lambda minus lambda. And all of the entries off the main diagonal are non-negative. So it has the same kind of properties that we expect from a Markov matrix in the finite state space setting, and we can and will formalize that. So there's a good concrete example of how a generator can be identified and how it works for a discrete space, continuous time Markov process. Before we get into some detail about structure theorems for these processes, I'd like to also briefly consider what might happen in the continuous time, continuous state space case. And for that, we will revisit our, what will be, favorite example, the Brownian motion. Again, we have not yet constructed Brownian motion. We've only constructed pre-Brownian motion, but that's all we need for these calculations here. This is a Markov process whose transition kernels are given by this Gaussian function right here. And I want to note right now that this transition kernel has a special name. It's called the heat kernel. Heat kernels are absolutely ubiquitous throughout mathematics, and if this is your first introduction to them, then boy, are you in for a treat, because we'll be dealing with them a lot for the rest of this course. Why is it called the heat kernel? Well, we'll understand that a little bit later on this slide. But for now, let's just note that this is the probability density of a normal random variable. Now, we can think about that as a normal random variable of variance t in the y variable, therefore having mean x, or alternatively, think of it as the density of a centered normal of variance t, but the variable being x minus y. And that's how we'll write it here. This is gamma t of x minus y. And then, as we saw before, the transition operator, which we get just by integrating our function against the heat kernel, is, by the form of this, the convolution of the Gaussian density with the function f. This is an example of what we would call a convolution semigroup. So the question, in the context of what we've talked about in this lecture, is there a Markov generator? That is, can we find an operator A, which is therefore going to act on the bounded Borel measurable functions on the real line, such that the operator qt here is e to the ta? Now, it's not even clear what that would mean right now, but we could at least ask for the differential equation, which we know has that as a solution in the finite setting. Can we find an operator A on bounded Borel measurable functions so that the derivative of qt of f is equal to a qt of f, and such that a and qt commute, so that that's also equal to qt of af. If we could find such an operator A, then of course right from here, if we set t equal to 0, since q of 0 is the identity, we would have that a is the derivative of the semigroup at time 0. And so that shows us that it's unique. Okay, so can we find such an operator A? Well, sort of. And here is the result. Suppose we take a test function, not in this large space of bounded measurable functions, but in the much smaller space of twice continuously differentiable functions with compact support. That is, of course, contained in the bounded measurable functions, but it is strictly contained. For such a function, you can find an a for which this differential equation holds, and that a is 1/2 the second derivative. So we would be tempted to say that the generator of Brownian motion is 1/2 the second derivative. And that is true when we appropriately define what a generator means in this context. And that, by the way, tells us why this is called the heat kernel, because what this equation therefore says, with this being 1/2 the second derivative operator here, is that this function of x and t satisfies the heat equation. The time derivative is 1/2 the second space derivative. That's the physics equation that governs the flow of heat in physical space, at least in one dimension. Now, the proof of this is on your homework. But the real delicate question is, does that mean that this is the generator of our process? By the way that we've defined it so far, we want a to actually be defined everywhere on the bounded functions. And if we want that to be true, then no. This process will not have a generator. It's not possible to find an operator defined everywhere on here that has this property here. And one way to see that is from the uniqueness here, because if such an operator did exist, then by uniqueness, if we restrict it to the twice continuously differentiable compactly supported functions, it would have to equal the one that we found here, 1/2 the second derivative. But from there, we can see that there will not be any extension of this operator that is defined everywhere here and spits out functions here that are still bounded. Why not? Well, for example, here's a function, the indicator of the unit interval, which we can write as a nice bounded limit of some bump functions. Bump functions that look like this. We've seen this construction over and over again. So there's psi n for some large n. And this sequence of functions will converge pointwise boundedly to this one. However, in so doing, these corners must develop. And when those corners develop, that means that taking the second derivative, we're going to get blow up. Turning a corner super sharply there means that our derivative, and we'll see higher derivatives as well, are going to blow up. And so you can see from there that there's no way that you could have an operator that acts like this on functions like this, and also acts in a bounded way on all bounded functions. So how do we deal with that? Well, we're going to delay the answer to that question until later in this course when we've developed much more technology. But the answer at the end of the day is that we will have to restrict our domain of test functions appropriately. It turns out that in the cases we're interested in, there will be a consistent way to do that, and we will be able to talk about generators of continuous time processes. The processes in question will be called Feller processes, a special class of continuous time Markov processes, which will be among the last topics that we cover in this course.